we're now ready to implement k-means clustering. So let's see what's going to happen. As usual, I'm going to import a bunch of libraries. This IPython display clear output, and this time is because I'm going to do an animation so I can see how the iterations of k-means are evolving. It's good for debugging. All right, let's generate a bunch of random data points. We're going to live in a two-dimensional space because that's where it's easiest to visualize, but obviously everything we're about to implement will work in an arbitrary dimensional space. So xpos is, again, let's call it the positive class, the blue class. Xneg will be the negative class. We're going to generate n data points of 2 dimensions, so x, y. And because I want these clusters to be separate from each other just for the purposes of easy visualization, I'm going to set the negative class to simply be the negative class to be simply the negative of the positive class. So the positive class will be a bunch of things in the first quadrant. The negative class will be in this quadrant down here, and then we're going to try to learn the various clusters. Okay, stack everything up into a single matrix, and notice here, unlike when we were doing supervised learning with LDA and SVMs, there is no class label. I've just packed all these together, and now I have 50 points, and that's all I know. And now my job is to find a label associated with each row of this now 50 by 2 matrix. 2 is the dimensionality of my data. 50 is each of the data points. Let's go ahead and plot everything and make sure I didn't do anything stupid here. And now let's compute the iterative k-means clustering algorithm. So I'm going to initialize by picking a random point out of that big data matrix. So C1 is some random row from the matrix. C2 is a random row from the matrix. And now I have I've hardwired the number of iterations to be 25. I didn't have to do that. I could have done this with a while loop and checked to see if I converge. I just chose to do this with the for loops. It made the code a little bit tighter. M is going to be my labels. Initially, everything gets labeled to be, there's n of these. That's the 50 data points. It's eventually going to be 1 or 2, depending on which class we're in. And what I'm going to ask is for the jth point, so this for loop here is going over all of the data points, look at the distance between the jth point and the current center and ask, is that less than or greater than the jth point from the second center? If it's less, then assign label 1. If it's greater, assign label 2. So this will do the class assignment or cluster assignment based on this initial cluster guess. Then we're going to re-estimate the cluster centers. How? Get everything that's labeled 1 and compute the center of mass. Get everything that's labeled 2, compute the center of mass. So we find all the indices in this matrix that are 1, all the indices that are 2, compute the center of mass of all those points that are labeled 1, all the points that are labeled 2. I've now got a new center, C1 and C2, visualize everything, sleep for a second, clear the display, and that's how I can do an animation. Run that over and over again. If you take that code, you'll actually see the animation, and this is where it stops right here. So let's see, we've got our two-dimensional space, 1, 2, x, y. Of course, the red points here were the class 1. That was the positive class. The blue points were class 2. That's the negative class. And that bright red point there is the center of the first class. And that bright blue point down there is the center of the second class. And we've done a pretty good job of learning these clusters. Now, this was an easy problem. After all, I've got the clusters separated. And I also, if you run this over and over again, sometimes it'll fail. Sometimes you'll get super unlucky, and what'll happen is you'll pick 2 points, for example, that are really far out here for your initialization. And what'll happen is it'll just never migrate 1 point down to here. So these techniques are extremely vulnerable, or can be extremely vulnerable, to the initial conditions. And so in practice, when you run k-means, you often, because it's so efficient, you're really doing nothing more complicated than computing a bunch of Euclidean distances and class assignments. You can if you have some intelligent way of bootstrapping, because maybe you have a couple of ideas of where the cluster centers are, you can do that. Or you can just run this algorithm over and over and over again with different random conditions, and then look to see what are the prevailing wins. That is, what are the most typical categorizations of each data point, and then the failures will simply integrate out, and the successes, when you get lucky enough to pick 2 points that are actually in the individual clusters, will start to trickle up to the top. Now, the other thing in practice that you have to worry about is, I assumed I knew 2 clusters. How do I know that there's 2? What if there's 3 or 4 or 10 or 12? We're not going to talk about it, but you should know that there are versions of k-means clustering that will allow you to start with a large number of clusters and then trim back down until the minimum ones that you need. And there's just some simple heuristics for doing that, for not having to assume that you know exactly how many clusters there are. Now, k-means clustering is one of those algorithms that has been around forever. It's a good algorithm to know, but in practice, unless you have relatively simple problems, it's not the most efficient and the most accurate and the most reliable technique. It's a good thing to always try at the beginning when you're doing unsupervised learning. You should know about it. It's everywhere in the literature. But there are more sophisticated techniques that we will be developing, but conceptually, they're going to build on this basic idea of k-means, which is why I like to introduce it in the beginning, but we'll take it from here when we come back.